Hello everyone, welcome to this lecture. We're gonna talk about continuous time and discrete time exponential signals, which are very important, and they are actually one of the key objects that are gonna appear later in this course. I am Touri, and I am with the Electrical and Computer Engineering Department at UCSD. So a continuous time exponential signal is any signal that we can write it as some constant times e to the power at. And here it's very important to note that c and a in general, they can be complex numbers. So the exponent a can be complex and the constant c can be complex. Often in these cases, it is very useful to write c in polar coordinate and write the exponent in the Cartesian coordinate. So if we do that, if we write c equals as beta times e to the j theta, and the exponent a to be alpha plus j omega naught, then xt becomes beta e to the alpha t times e to the j omega naught t plus theta, where now alpha and beta are both real numbers, real values, and beta is actually positive. Alpha is a real number. It can be negative, but it's a real number. And then we have a pure imaginary exponent, e to the j omega naught t plus theta. If alpha is less than 0, then we have a decaying exponential. So as t goes to infinity, we have a signal that goes to 0. And when t goes to negative infinity, the signal goes to infinity, blows up to infinity. And it is very important to note this, that for any exponential, even if the alpha is negative, when t goes to negative infinity, it goes to infinity. So other important case, so the oscillatory behavior, the decaying behavior of this exponential, as I mentioned, is related to the real part of the exponent, a, which is alpha, the way that we wrote it here. And the oscillatory behavior actually is related to omega naught. So if omega naught is 0, then we don't have any oscillation. So it's a pure exponential, real valued exponential. And if omega naught is not 0, then we have an oscillatory signal. The phase of c, which is the angle of c, actually tells us the phase of this whole exponential. And if alpha, the real part of a, is just 0, then we are dealing with a pure complex exponential signal. In this case, xt can be written as some a cosine of omega naught t plus theta plus j a sine of omega naught plus theta, where again theta is the angle of the constant c. And in this case, the fundamental period, we're dealing with a periodic signal, and the fundamental period, as you've learned from the previous lectures, is going to be 2 pi over the absolute value of omega naught. For the real exponentials, again, we have the imaginary part of a is equal to 0, and a is purely a real number. So when a is positive, then we are having an exponentially increasing, and when a is negative, we have the exponentially decreasing signal. Similar to the continuous time, we can define pure complex exponential signal in discrete time to be xn of the form c some constant times e to the beta n. But it is often very useful in discrete time to absorb e to the beta to another variable z and look at exponential signals in discrete time as some constant times z to the n. The two forms are actually equivalent, but this form is more useful in discrete time. The other form, where you're writing everything in base e, is more useful in the continuous time. So in discrete time, again, we're looking at signals that are formed c times z to the n. And again, there are multiple cases. The pure real valued exponential, where both c and z are real valued. In this case, if z, so remember that xn is cz to the n. So if absolute value of z, so z is in general a complex number. So if absolute value of z is less than 1, or in other words, z is inside the unit circle on the complex plane, then if I look at the absolute value of xn, we have an exponentially decreasing signal. And absolute value, in the case that absolute value of z is greater than 1, or in other words, z is outside the unit circle, we are dealing with an exponentially increasing signal. The other case is when z is actually on the unit circle. So we talked about the case that z is inside the unit circle. We talked about the case that z is outside the unit circle. And now the case that z is on the unit circle is also an interesting case. It's interesting to think about when such a signal is periodic. To have a periodic signal, we need to have some capital N, such that xn plus capital N equals xn. So let's investigate this. Again, we are investigating under what condition these pure exponential signals are periodic. So in this case, so what we will have is that we need to have c e to the j omega naught n plus capital N should be equal to c e to the j omega naught n, and we can cancel out c e to the j omega naught n because c e to the j omega naught n is a non-zero number, so we can cancel it from the both sides of this equation to get that e to the j omega naught n equals to 1. It's an interesting question that under what condition, for what values of omega naught there exists some capital N that this is equal to 1. So we know that e to j theta is equal to 1 if and only if theta is some multiple of 2 pi. So therefore, to have omega naught n to be such that e to the j omega naught n equals to 1, we need that omega naught n to be some multiple of 2 pi, so 2k pi, where k is an integer. Or in other words, omega naught should be k over n 2 pi, which means that such an exponential, where z is on the unit circle, is periodic if and only if omega naught is some rational multiple of 2 pi. All right, so this was the discussion on discrete time and continuous time exponentials. Thank you for watching.